There is one thing that is almost always true in a science like astronomy. When you have a new scientific instrument or telescope, wherever you look, you are bound to discover new details you have never seen before, even if it's an object you have observed thousands of times before. This aptly describes the scientific breakthroughs provided by the James Webb Space Telescope in just 2 years of operation. Of course, its primary goal was to expand the horizons of our observations, making the early universe and the peculiar galaxies inhabiting it the first and most striking discoveries during this time. However, it wasn't just the cosmic dawn that proved groundbreaking. The atmospheres of exoplanets, the intricate physics of star formation, and even some previously unknown features of our solar system have been unveiled thanks to this new space observatory. In this second part of our review of recent scientific achievements, we will discuss precisely these discoveries. Be warned, there's a lot to cover, so make yourself comfortable. The first testing ground for assessing Webb's capabilities in studying exoplanets was a massive hot gas giant named WASP-39b. This planet, about the size of Saturn and located 700 light-years away, orbits its star closer than Mercury orbits the Sun. As a result, it has a puffy, extended atmosphere, through which starlight provides a strong enough signal for chemical analysis. This is what is called a transmission spectrum. In simple terms, astronomers split the system's light into a spectrum and analyze it. They do this at least twice. Once when the planet passes in front of its star, when starlight shines through its atmosphere, and again when the planet is not transiting, leaving the star's spectrum unobstructed. By comparing the two spectra, astronomers can identify which chemical compounds are present exclusively in the atmosphere, as well as determine the temperature and other properties of the planet. Previously, WASP-39b had been observed by other telescopes, such as Hubble and Spitzer, which allowed astronomers to detect certain compounds. However, in its first months of operation, JWST provided a nearly complete recipe for the planet's atmospheric composition, even revealing signs of clouds driven by powerful winds. It detected substances like sodium, potassium, water vapor, and carbon monoxide, along with a very strong signal from carbon dioxide, captured with far greater resolution than ever before. Moreover, astronomers for the first time detected sulfur dioxide in the atmosphere of an exoplanet. This compound forms as a result of high-energy radiation from the star interacting with the atmosphere. A similar process occurs on Earth, where photochemical reactions create the ozone layer in the upper atmosphere. This marked the first observation of photochemistry on another planet. In July 2024, as part of another study, a team of scientists went beyond determining the basic properties of the atmosphere and managed to examine a specific part of it, called the terminator, the boundary zone between the day and night sides of the planet. Since the planet is tidally locked, one side perpetually faces its star, while the other remains in eternal darkness. Previously, it was believed that the structure of atmospheres at terminators should be uniform. Over the past decade, however, astronomers began to suspect that there must be a difference between the terminator where the atmosphere circulates from the night side to the day side and the opposite one, where it leaves the day side and plunges into night. Yet no confirmation of this theory had been found. Using the near-infrared spectrograph, better known as NIRSpec, astronomers managed to obtain two distinct spectra from the morning and evening terminators of the planet. They concluded that the temperature difference between them is about 200 degrees. That is, the evening terminator was hotter than the morning one. This can be explained by the fact that on the morning side, the atmosphere has already had time to cool down as it moves across the night side. By the time it reaches the day side, it heats up and crosses the evening terminator while still retaining more heat. This was the first confirmation of models explaining atmospheric dynamics on tidally locked planets. Another world Webb turned its gilded mirror toward was not as hot. In fact, quite the opposite. It was one of the coldest worlds studied so far. Epsilon Indi Ab, the first exoplanet directly imaged by James Webb, meaning it was captured in an actual photograph. This cold gas giant is relatively close to us, about 12 light-years away. Interestingly, if inhabitants of neighboring star systems had a space telescope similar to Webb and looked toward the solar system, they might see something very similar to what is shown in this image. That's because the star is a K-type, slightly smaller and cooler than the Sun, and its planet is very similar to Jupiter. However, it is 100 degrees warmer than Jupiter and 6 times more massive. To date, only a few planets have been directly imaged, and Epsilon Indi AB is the coldest of them, with a temperature of about 2 degrees Celsius. This is quite an achievement. The challenge lies in the fact that previously imaged exoplanets were generally younger and still radiating significant leftover energy from their formation. As planets cool and contract, they emit less radiation, making them harder to observe. Most of their emission shifts into the mid-infrared range, where James Webb, with its MIRI mid-infrared instrument, excels. Using the coronagraph installed on this instrument, a team of astronomers managed to reveal a world that had previously remained hidden. Given the planet's similarities to Jupiter, this provides a rare opportunity to study atmospheres of true analogs to planets in the solar system. Interestingly, Epsilon Indi AB had been detected earlier through the indirect radial velocity method, or Doppler technique. However, the planet that was imaged turned out to differ significantly from the parameters estimated using the Doppler method. The actual planet was twice as massive, orbited slightly farther from its star, and had a completely different orbit than initially predicted. Naturally, this raises the possibility of another unseen world in the system. Yet, according to the researchers, this newly imaged planet is the dominant source of the star's gravitational wobble, leaving the discrepancy with earlier predictions as an unresolved mystery. Perhaps our indirect detection methods don't always provide the precision we'd like. Nevertheless, it was the Doppler method that first hinted at the presence of something in the system, serving as a critical motivator for observing it with Webb. So while the exact characteristics of the planet might not align with earlier estimates, the method remains highly reliable in confirming the presence of at least some object orbiting the star. Another, perhaps the most well-known method for discovering exoplanets is, of course, the transit method. Here, the TESS Space Telescope currently dominates, searching for sudden dips in a star's brightness when a planet passes in front of it, blocking part of the light. One of its candidates, named LHS 475b, caught the attention of a team of astronomers from Johns Hopkins University who aimed to test the capabilities of the James Webb Space Telescope in studying Earth-like planets. Preliminary data suggested that this world, located 41 light-years away, is indeed Earth mass and orbits a faint red dwarf star. However, test data only hinted at its existence, as the satellite's cameras are limited in capability and the signal was extremely weak. The near-infrared spectrograph aboard Webb clearly confirmed the planet's existence after just 2 transit observations. This breakthrough occurred in the summer of 2022, shortly after Webb began operations. Thus, the planet's existence is indisputable, and it became the first exoplanet confirmed by JWST. But the real goal for scientists wasn't merely to confirm the planet's existence. They wanted to determine whether this world has an atmosphere. That's the most intriguing aspect of Earth-like planets. Nowadays, detecting atmospheres around exoplanets dozens or even hundreds of light-years away isn't as extraordinary as it once seemed. The atmospheres of gas giants, especially hot, bloated ones, are relatively easy to detect. The Hubble Space Telescope first achieved this in 2001. However, much smaller and denser atmospheres around rocky planets, which are themselves tiny compared to gas giants, remain elusive. Yet these Earth-like worlds are what interest us most, aren't they? As lofty as it may sound, JWST is the only telescope currently capable of characterizing such atmospheres. Thus, LHS 475b became another testing ground. Using near-spec, the team obtained the planet's light spectrum, but unfortunately, the results didn't provide definitive answers. In essence, Webb didn't detect significant amounts of any specific chemical element or molecule. This ruled out a puffy hydrogen-dominated atmosphere. Astronomers also ruled out a methane-rich atmosphere, represented by the green line in the graph, which would block more starlight at this wavelength. The yellow line shows the best-fitting model, which, unfortunately, corresponds to a bare rock, essentially the complete absence of any atmosphere. However, there's also a purple line that cannot be ruled out based on current data. This line represents a model with a thin carbon dioxide atmosphere, which is challenging to distinguish from a bare rock given the current precision. Carbon dioxide is relatively heavy, so if such an atmosphere exists, it is likely very thin and exceptionally difficult to detect, requiring even more precise measurements. As you can see, even for JWST, this remains a challenging task. Typically, it's not enough to merely obtain a system's spectrum. Sophisticated modeling is also required to determine which type of atmosphere best fits the observations. This field is still in its infancy, and astronomers have a great deal of work ahead of them. Perhaps the best attempt so far to detect the atmosphere of a terrestrial-like planet was made by researchers from NASA's Jet Propulsion Laboratory. Using the James Webb Space Telescope, they observed a world named 55 Cancri E, likely a super-Earth located 41 light-years away from us. This is a well-known planet, discovered back in 2004 using the Doppler method, and it is one of 5 known planets in this system. Since its discovery, it has been the focus of numerous studies, with researchers attempting to find traces of an atmosphere using various methods. The interest stems from the fact that the system is relatively close to us, and the planet is nearly twice the size of Earth and about 9 times more massive. Given its density, it is considered a rocky world, making it especially intriguing. The orbit of 55 Cancri E is 25 times closer to its Sun-like star than Mercury's orbit is to our Sun, making it almost certainly a hellish world with a surface covered in flowing molten lava. Using the Spitzer infrared telescope, astronomers previously detected hints of a weak envelope around the planet. However, they couldn't determine whether it was a full-fledged atmosphere or simply vaporized rock. To resolve this question, a group of scientists turned to JWST and its 2 instruments, NIRCam and MIRI. They measured the amount of thermal infrared radiation coming from the planet using the secondary eclipse technique. In simple terms, astronomers measured the system's total radiation when the planet was hidden behind the star's disk, and compared it to the radiation when the planet was visible next to the star. In the latter case, the planet's radiation adds to the star's brightness. By subtracting the brightness of the star alone from the combined brightness of the star and planet, they isolated the amount of energy emitted solely by the planet. Incidentally, this same method was used to assess the presence, or rather the absence, of atmospheres on nearby planets in the TRAPPIST-1 system. How does the amount of a planet's energy emission reveal its atmosphere? This requires modeling. Astronomers know that if a planet lacks an atmosphere or only has vaporized rock, it should be extremely hot. According to their calculations, its temperature should be around 2,200 degrees Celsius. However, the amount of radiation measured by the MIRI instrument indicated a much lower temperature, approximately 1,540 degrees Celsius. This suggests that heat is being efficiently distributed across the planet's surface, which would only occur if there were a full-fledged atmosphere rich in volatile substances. Moreover, data from NIRCam, marked as orange points on the graph, revealed a significant dip in the spectrum at wavelengths corresponding to absorption by carbon monoxide and carbon dioxide. A planet without an atmosphere simply wouldn't show such spectral features. Overall, the infographic shows that the model with an atmosphere, represented by the blue curve, aligns better with the observations than the model without one. This makes it the best evidence we currently have for the atmosphere of a rocky planet. Clear chemical signatures of the atmosphere of an Earth-like planet, which we are all eagerly awaiting, remain a matter for future research. There is an object in the night sky known to every amateur astronomer and to anyone who occasionally gazes at the stars. This is the closest star-forming region to Earth, widely recognized as the Orion Nebula. Here, from clouds of dust and gas, thousands of newborn stars ignite, often accompanied by planetary systems. Thanks to its brightness and relative proximity, just 1,350 light-years from Earth, the Orion Nebula has, for decades, been a treasure trove of astronomical discoveries. From ionized gas clouds to protoplanetary disks, young stars, and even substellar objects. It is in this well-studied patch of sky that the James Webb Space Telescope has uncovered one of the greatest mysteries about star and planet formation. This is how the nebula appears in images captured by the near-infrared camera. Beyond its undeniable beauty, this image reveals far more details than were previously visible. While earlier space and ground-based telescopes had identified a large population of brown dwarfs, objects of lower mass, such as Jupiter-sized planets, remained rare and typically invisible to those instruments. This is because even at a relatively young age, planets are cooler than brown dwarfs and emit most of their energy in the thermal infrared range of the spectrum. So, when a team of astronomers turned the infrared gaze of JWST toward the Orion Nebula, It's unsurprising that they were able to find hundreds of new planetary mass objects. Specifically, they identified 540 candidates with masses below 13 Jupiter masses. Of these, 168 exhibited methane absorption lines, consistent with models of planets with masses around 5 Jupiter masses or even less. This, in itself, is remarkable, a discovery of so many planets not gravitationally bound to any star, another confirmation that free-floating planets are practically everywhere. However, the most unexpected result was that a significant fraction of these candidates were binary systems, orbiting in pairs. Approximately 40 such pairs were identified, and 2 systems were found to consist of 3 components each. This result is highly unusual and, in fact, challenges the established principle of the distribution of multiple systems in the universe as observed by astronomers. Here's the issue. It seems that more massive stars have an easier time forming binary systems compared to lower mass stars. There are several potential explanations. During the initial stages of formation, when gas clouds collapse and heat up, they may form multiple dense regions, and the more massive regions are better able to attract surrounding material or form multiple components. Additionally, already formed massive stars are better at maintaining stable systems in dense, crowded regions like the clusters where they are born. Lower mass binary stars, on the other hand, may break apart in such environments. Any disturbances can cause them to drift apart. According to observations, more than 75% of massive stars indeed exist in binary systems. However, for stars with a mass similar to the Sun, this percentage is an order of magnitude lower, approximately 50 to 60% form pairs. For red dwarfs, the percentage is even smaller, ranging from 20% to 30%, while for brown dwarfs, it drops to 15% or even as low as 8%, depending on their mass. Based on this logic, much less massive free-floating planets should form binary systems almost never, or at least not often enough to identify 4 dozen of them in just one nebula. Okay, but this assumes they are born this way. It's widely accepted that starless planets don't necessarily have to be born alone. They could have originated as part of a planetary system around a full-fledged star, but were, for instance, ejected due to gravitational disturbances. And while this could explain their solitary nature, could it also apply to binary systems? It's hard to imagine a set of circumstances in which 2 planets would be ejected from the same system while maintaining their mutual gravitational bond. This makes the discovery of these 40 binary Jupiters a staggering revelation, effectively a new class of objects now referred to as jumbo, short for Jupiter mass binary objects. These jumbos may challenge our understanding of both stellar formation theories and planet formation theories. So what's going on here? As you've probably guessed, no one knows for sure why free-floating planets form pairs, but several explanations have been proposed. One possibility prompts us to view these objects as failed stars. Perhaps the clumps of matter that collapsed within the nebula were not massive enough to ignite nuclear fusion. Star formation is essentially a race. The faster a clump accumulates mass, the more likely it is to ignite. Those that lag behind may fail to grow into full-fledged stars. Newborn stars emit copious amounts of ultraviolet radiation, which influences the surrounding material, essentially blowing it away like a cosmic wind. Thus, slower-growing clumps have a high chance of falling short of the mass needed to ignite fusion, potentially leaving them as mere planets. Their already formed, brighter stellar neighbors can deprive them of the additional matter needed for growth. Objects that fail to accumulate sufficient mass remain in a sort of stunted developmental stage, and perhaps these are what we now observe as free-floating planets. It's also possible that they were once normal stellar systems disrupted by intense radiation during their formation. On the other hand, a study from April 2024 modeled conditions under which pairs of gas giants could be ejected from a single system. The researchers concluded that in densely populated regions, such as stellar clusters where stars and planetary systems frequently interact, such a scenario is indeed possible. This would require 2 planets within the same system to align with one another at some point. If, during this alignment, the system experiences gravitational influence from another star, it could disrupt the planet's dynamics. As a result, both planets could be ejected from the system, and due to their relative proximity, they might even form a binary system. Yes, I agree that this scenario seems a bit contrived, but the author's modeling is quite convincing. In an environment like the Orion Nebula, it cannot be ruled out. In any case, it seems that planet formation is a far more diverse and fascinating process than previously thought. The The sensitivity of the James Webb Space Telescope has, for the first time, allowed the discovery of an entirely new class of objects. Apart from the Orion Nebula, there is another remarkable celestial object where the Webb telescope has unveiled new, previously unseen details. This is Fomalhaut, one of the brightest stars in the night sky. It is an exceptional star because, like Vega or Epsilon Eridani, it still retains a protoplanetary disk from which planets are forming or have already formed. This was discovered at the dawn of infrared astronomy when NASA's IRIS satellite detected an excess of infrared radiation in such systems. It quickly became evident that this infrared glow indicated large amounts of heated dust and debris surrounding the stars. Later, observatories like Hubble and the ALMA interferometer revealed a vast debris ring in the Fomalhaut system, a finding confirmed by observations from the Spitzer telescope. Positioned at a distance of 140 astronomical units from the star, this structure is unequivocally regarded as analogous to our Kuiper belt. If scientists correctly understand the evolution of planetary systems, such belts are shaped by the gravitational interactions of one or several young planets. Similarly, Jupiter shaped the asteroid belt, and Neptune delineated the inner edge of the Kuiper belt. Hence, searching for a planet in this system was a promising endeavor. When astronomers closely examined the disk's images, they noticed a distinct, bright clump that strongly resembled a large gas planet. However, as the system was observed over time and across multiple wavelengths, it became clear that the clump, initially named Fomalhaut B, gradually expanded and dimmed. This behavior is not typical for a planet but is reminiscent of a cloud of debris resulting from the collision of two objects, such as icy planetesimals. Over time, the cloud dissipated entirely, vanishing by 2014. Nevertheless, in May 2023, a team of scientists decided to observe the Fomalhaut system using the James Webb Space Telescope. Many anticipated that this instrument would finally reveal the disk's inner structure, where terrestrial-like planets are born. All prior attempts at direct observation of protoplanetary disks had been limited to their outer edges. Since Fomalhaut is only 25 light-years away, Webb's MIRI instrument indeed captured new details. First, the old cloud previously mistaken for a planet was truly gone, but intriguingly, a new one seemed to have appeared. This indicated that the young system is an extremely dynamic environment where large objects frequently collide. Second, moving closer to the star, Webb revealed another distinct gap in the inner disk, which had not been visible before. This discovery showed that the system not only features a Kuiper belt and an inner belt resembling the asteroid belt, but also includes a third intermediate belt with no known counterpart in our solar system. Interestingly, the newly discovered gap is smaller and much narrower than the outer one, meaning its formation might not require a gas giant like Jupiter. Instead, it could have been carved out by something akin to Neptune or several smaller planets, potentially Earth-like. Thus, astronomers gained the unprecedented ability to study debris disks around young stars with such detail, including their inner regions, where Earth-like worlds are born. Another spectacular nebula, Rho Ophiuchi, has also come into the spotlight of the world's premier space telescope. It is called a dark nebula because dense clouds of gas block much of the visible light. As a result, James Webb captured many previously hidden details, the most striking of which can be seen in the upper left of the image. These are bright jets of gas ejected from newborn stars, slamming into the surrounding gas. While such structures are not new and have been observed before, they are somewhat special in this nebula because almost all the jets share a remarkably similar orientation. In other words, the young stars seem to have aligned themselves in one direction, shooting their gas jets in the same way. Although this looks unusual and has never been seen before, the phenomenon was predicted. It serves as an excellent example of how scientists' models can foresee phenomena before they are observed in the real universe. As you may know, stars form in molecular clouds, dense regions of interstellar dust and gas. These clouds often have an elongated shape, stretching across several light-years, earning them the name filaments, much like elongated clusters of thousands of galaxies. Significantly, these clouds have angular momentum, meaning they rotate in a specific direction, likely influenced by external gravitational forces or magnetic fields. Consequently, clumps of matter within these clouds, which accumulate mass and rotate, inherit the angular momentum of the parent cloud. As a result, all these clumps tend to spin in roughly the same direction. When they grow into full-fledged protostars with their own accretion disks, their orientation remains consistent, still reflecting the angular momentum of the original cloud. The jets captured in Webb's images are streams of gas escaping from the accretion disks of young stars, guided by powerful magnetic fields. These fields channel the gas along the poles of the star, ejecting it from the system where it collides with the surrounding material. The fact that all these jets on Webb's image are similarly aligned points to the shared origin of their parent stars. They are likely clumps of matter formed within the same molecular cloud and inherited its angular momentum. The probability of such alignment occurring by chance is extremely low. The researchers estimate it to be about 1 in 10,000. This alignment represents a special moment in the nebula's history. Over time, gravitational interactions between the individual stars will eventually cause the jets to deviate from their shared direction. But for now, they appear strikingly similar. By the way, check out this stellar jet in the constellation Perseus. It's important to understand that such objects are still embedded within the gas clouds they formed from, and only Webb's infrared sensitivity allows us to uncover such detailed views of star formation. Of course, it also lets us enjoy the breathtaking cosmic landscapes. The death of stars can be just as fascinating and spectacular as their birth. Supernova explosions are arguably the most awe-inspiring releases of energy in the universe. The challenge, however, is that most supernovae are faint, distant points of light millions of light-years away. The last supernova observed in our galaxy was recorded by Johannes Kepler in the 17th century. However, after 400 years, astronomers finally got lucky. In 1987, a star in the Large Magellanic Cloud, a dwarf galaxy neighboring the Milky Way, located about 160,000 light-years from us, suddenly exploded. SN 1987A was first observed from Earth in February of that year, reaching its peak brightness by May. A supernova visible to the naked eye naturally became a top priority for detailed observations with telescopes. Over decades, astronomers tracked the aftermath of this event in real time, using instruments across nearly the entire electromagnetic spectrum, from X-rays to radio waves. Despite these exhaustive studies, one question remained unanswered. What exactly did the star's core transform into? There are two possibilities. Either a new stellar mass black hole was born, or it became a dead stellar remnant known as a neutron star. Scientists have long searched for evidence of this compact object, and some indirect evidence pointed to the latter, a young neutron star hidden at the core. To confirm this, a team of researchers turned James Webb's mirrors toward the supernova. Notably, SN 1987A was one of the telescope's first targets. Its scientific observations began on July 12th, and by July 16th, Webb was already collecting light from the supernova. The team utilized the MIRI instrument in its integral field spectroscopy mode. This is essentially a specialized device that not only captures an image of the object, but also provides its spectrum. The image is divided into separate segments, allowing astronomers to obtain a light spectrum for each pixel individually. This technique enables the identification of spectroscopic differences across various parts of a single object. Spectral analysis of the supernova remnant revealed a strong signal from ionized argon originating from its central region. Further observations using the NIR-SPEC instrument detected even more ionized elements. Such findings indicate the presence of high-energy radiation capable of stripping electrons from atoms. But what could be the source of this radiation? In their study, the authors explored various scenarios, including the possibility of a companion star that survived the explosion. However, all alternative explanations were ultimately ruled out. The only plausible scenario consistent with the observations is the presence of a young neutron star ionizing the surrounding gas. While this is not a direct observation of the stellar remnant, it is nonetheless compelling evidence that astronomers in 1987 not only witnessed the powerful explosion of a star, but also the birth of a neutron star. Of course, young stars with gas and dust disks are of particular interest to astronomers, as many questions about the formation of the solar system remain unanswered. One of the most significant of these questions concerns life, how it arose here, and whether it might exist elsewhere. In search of answers, scientists carefully observe young stellar systems, aiming to detect the key chemical ingredients for life: complex organic molecules. These molecules are considered complex because they contain at least 6 or more atoms, including at least one carbon atom. After all, if life without carbon exists, it remains unknown to us. It should be noted that complex organic molecules in space are not rare. They have been found in abundance, particularly in protostellar systems. However, most of these molecules exist in the gas phase, whereas scientists are particularly eager to observe them on the surfaces of solid particles. The reason is that when embedded within ice particles, organic molecules are better shielded from harsh stellar radiation and can more easily migrate deeper into young systems, to the regions where rocky planets are likely to form. Moreover, solid-phase chemical reactions on the surfaces of dust particles are more efficient at producing complex types of molecules. Finally, these grains serve as building blocks for comets and planetesimals, meaning that organic molecules can become incorporated into planets or their atmospheres. Since these icy grains also contain water, their journey alongside organic compounds enhances the chances for the recipient planet to become habitable. The challenge is that, until recently, only methanol had been reliably identified in the solid phase, while other molecules remained hidden. In one of the early scientific programs of the James Webb Space Telescope, astronomers studied young stellar systems in their protostar phase using Webb's MIRI instrument. Among the dozens of systems examined, 2 finally revealed what scientists had long been hoping to see. Webb discovered a rich assortment of both simple and complex organic molecules in the solid phase, including ethanol and acetic acid. Particularly intriguing is the Iris-2A source, characterized as a low-mass protostar. In other words, it could represent an early stage in the formation of a sun-like star, with the surrounding chemical compounds potentially resembling those present at the dawn of our solar system. This is a profoundly significant discovery, but that's not all. In 2023, a group of scientists using Webb identified a molecule in space for the first time known as the methyl cation. This molecule is particularly important because it acts as a kind of connector for various substances, readily reacting with a wide range of other molecules to form more complex compounds. Thanks to this property, the methyl cation may serve as a cornerstone of interstellar organic chemistry. Webb detected this molecule in a young system with a protoplanetary disk known as D-200-3506. Notably, this system is located in none other than the Orion Nebula. It's not just deep space objects like galaxies, stars, nebulae, or exoplanets that captivate scientists and space enthusiasts. From personal experience, I know that the solar system ranks among the favorite topics of my audience. Scientists, too, are trying to answer numerous questions about the planets in our system and other fascinating objects like moons, dwarf planets, comets, asteroids, and ring systems. So, how can the James Webb Space Telescope help in this regard? First, we need to recognize Webb's limitations. The telescope cannot observe any objects located closer to the Sun than itself. The intense thermal radiation from our star could overwhelm its sensitive infrared instruments. Thus, Mercury, Venus, Earth, and the Moon are off-limits for Webb. However, starting with Mars, Webb's spectroscopic capabilities become incredibly useful. Webb first turned its gaze to the red planet on September 5, 2022. Observing Mars, however, poses a unique challenge. The planet is one of the brightest objects in the night sky, both in visible and infrared light. For Webb, Mars is almost blinding, causing detector saturation. To overcome this, astronomers use the shortest possible exposure times, collecting minimal light, and apply advanced data analysis techniques. Even with these measures, Mars often appears overexposed in Webb's images. One such image, captured by Webb's NIRCam instrument, showcases the thermal energy Mars emits as it loses heat. The brightest spot corresponds to the area of the surface most heated by the Sun. Importantly, light leaving Mars passes through its thin atmosphere, offering a valuable opportunity for Webb to analyze the planet's chemical composition. Webb easily detects spectral signatures of water, carbon dioxide, and carbon monoxide in the Martian atmosphere, though unfortunately it has yet to identify traces of methane. Methane is particularly intriguing because it mysteriously appears and disappears in data from instruments like the Curiosity rover and the ExoMars orbiter. Methane on Earth can be produced not only by geological processes, but also by living organisms, making it a key target for astrobiology. Beyond methane, Webb's data provides insights into Martian dust, icy clouds, surface rock types, and atmospheric composition. Its spectral capabilities also allow for the study of transient phenomena like dust storms, weather conditions, and seasonal changes on the red planet. Auroras, storms, the Great Red Spot, moons, and even faint rings. This is how Jupiter appeared in images captured by the James Webb Space Telescope. This composite image, created using Webb's NIRCam instrument across multiple infrared filters, offers a new perspective on the largest planet in our solar system. While Jupiter has been extensively studied by numerous telescopes and orbital probes, each providing new details in different wavelengths, Webb's observations extend further into the near-infrared spectrum than ever before. This allows it to be more sensitive to higher atmospheric layers, 50 kilometers above Jupiter's cloud tops. In 2023, scientists analyzing this image uncovered a previously unseen feature, a high-speed jet stream approximately 4,800 kilometers wide. Located above the equator in the lower stratosphere at an altitude of about 40 kilometers, this jet moves at a staggering speed of 515 kilometers per hour. Thanks to Webb's precision, what once appeared as a diffuse haze now reveals distinct features that scientists can track. Even after decades of research, Jupiter's atmospheric dynamics continue to surprise us with the new details. One of Webb's wide-field images showcases Jupiter's faint rings, which are at least 1 million times dimmer than the planet itself, and notoriously difficult to detect. The image also includes 2 small Jovian moons, Amalthea and Adrastea. The spotlight naturally shifts to Europa, widely regarded as Jupiter's most fascinating moon. Webb turned its attention to Europa, yielding significant findings despite the moon's small size. The NIRCam image of Europa is not sharp or visually spectacular, as Europa's angular size is minuscule compared to galaxies Webb often observes. Even galaxies hundreds of millions or billions of light-years away occupy a larger apparent area in the sky than Europa. Thus, it's no surprise that Webb's direct images of the moon are reduced to blurred pixels. Yet, those pixels are a goldmine for spectroscopy. Webb's NIRCam, like the MIRI instrument, can simultaneously image an object and determine its chemical composition, even for individual pixels. Each pixel in this image represents an area 320 by 320 kilometers on Europa's surface. In September 2023, scientists analyzing these data identified carbon dioxide on Europa's surface, concentrated in a region known as Terra Regio, formerly chaos terrain. This relatively young area is thought to be geologically active, with surface ice disrupted and exchanged with material from the subsurface. The Hubble Space Telescope previously detected signs of oceanic salts in this area, and Webb now confirms a concentration of carbon dioxide. Importantly, carbon dioxide is unstable on Europa's surface, meaning it must have been delivered recently through geological processes. The combination of a young surface, salts, and carbon dioxide strongly suggests that these materials originate from Europa's subsurface ocean. This is a groundbreaking conclusion, as it implies a chemically rich ocean, conditions that significantly improve the prospects for life as we know it. Remarkably, Webb required only a few minutes of observations to deliver these transformative scientific results. They reinforce Europa's status as one of the most intriguing places in the solar system. Future missions, including NASA's Europa Clipper and the European Space Agency's JUICE, are on their way and expected to provide even more insights in the 2030s. Meanwhile, Webb's observations also sought evidence of water vapor plumes on Europa, previously spotted by Hubble in 2013, 2016, and 2017. However, detecting such plumes proved to be challenging this time. Instead, another icy world orbiting Saturn truly impressed in this component. This is an image of tiny Enceladus captured by the NIRSpec instrument, and in fact, the moon itself is just a single pixel highlighted in red. The rest of the image shows a massive plume of water erupting from its surface. It is 20 times larger than the moon itself and extends over 10,000 kilometers into space. Scientists were initially skeptical when they observed the scale of this eruption and the amount of water fueling nearly the entire Saturnian system. Orbiting the planet every 33 hours, Enceladus leaves behind a water halo resembling a donut or a water torus located near Saturn's widest ring, the E ring. About 30% of the water the Moon constantly spews remains in this torus, while the remaining 70% disperses throughout the Saturnian system. Unlike Europa, there are currently no new missions planned for icy Enceladus, making the James Webb Space Telescope the primary tool for observing it in the coming years. As for the planet itself, Saturn has also been in the focus of the Space Observatory. As you might notice, it is not as bright in the infrared spectrum as Jupiter. This is because methane in its atmosphere absorbs almost all the light reaching the planet, and Saturn emits less light and is cooler than Jupiter. However, its rings remain relatively bright, giving it an unusual appearance. The rings are also vividly visible in a portrait of Uranus captured by the NIRCam instrument. This planet doesn't emit or reflect much infrared light either, but several of its fascinating features are still visible. Notably, the seasonal northern polar cap is quite distinct. As Uranus approaches its solstice in 2028, these structures will change, and astronomers are eager to observe their dynamics. Additionally, Webb has managed to capture the planet's faint outer and inner rings, including the elusive Z ring, which is extremely faint and closest to the planet. Many of Uranus's 27 moons also fell within the telescope's sights. The other icy giant and the last planet in the solar system, Neptune, is also quite dim in the infrared spectrum with the exception of its clouds. Methane in Neptune's atmosphere absorbs infrared radiation, but its methane ice clouds appear as bright streaks and spots because they reflect sunlight before it is absorbed by gaseous methane. The bright star-like object in the upper left is Triton, which shines brightly because it reflects much more infrared light than the planet itself. Overall, both icy giants remain poorly studied, as only Voyager 2 visited them in the late 1980s. Therefore, almost every new piece of information we learn about Uranus and Neptune significantly contributes to our understanding of these worlds. Since there are no current missions planned for the icy giants, progress in exploring this crucial class of planets will rely on Webb and potentially its successors. Well, I guess that's all I wanted to share with you today. Thank you for watching until the end, and thank you for supporting my work with a like and a comment. See you in the next episode.